So in this video, we'll be working on a simple project using our STM32 Nucleo board and using a I2C LCD so that we can control the cursor position of our LCD and the characters or the text to be displayed in the LCD using a serial application program. In my case, I'm using RealTerm, and this can be done using the UART peripheral of the STM32 with direct memory access or DMA. So stay tuned and let's work on this together. So again, welcome, and as you can see in our preview, we'll be working on a simple project uh, that uses peripherals UART and I2C. So go ahead and open your STM32 Cube MX and let me just yeah. So before I begin, I am using a STM32F446RE in a Nucleo board, and these are so as you can see there, it is already configured. The pins are already configured. This is just to save some time, but don't you worry, I'll uh, discuss every setup step by step. So from here, again, I am using the default setup from my board, and these are the default setup right here, beginning from the PC13, where is my push button is connected, and it is configured as a GPIO external interrupt, and the pins right here are basically for selecting the clock source, and the default setup from my board uses an external clock, um, which are the configurations right here for the RCC oscillator. And for the green LED, PA5, which is the analog output. And these are again is up to you if you want to configure these. But it's a good habit or practice that you want to configure these one, um, even though you're not using it. So just will help you remind that these there are onboard buttons and LEDs on your board. So without further ado, again, we are working on our primary peripheral for today, which is the UART, and UART with direct memory addressing or DMA, and we are also using I2C connection right here for our LCD display. So let's go ahead, and before I begin, it is always good to have it whenever you're working on a project, go on you will enable the assist serial wire, serial wire and sysdig. This is because this enables debugging for your board, and yeah, you of course you want to whenever you're working on a project on your STM32, you're continuously debugging your project to look out for bugs and that. And yeah, even though you're not using it, again, I highly encourage to enable that because you might never know whenever you will across a bug. So now let's go into our main peripheral, go on to connectivity, and let's first work on with the USART or UART. So select USART2. The reason why we select USART2 other than the USART1 and USART3 and USART6 and other UART4 and 5 is because USART2 is the peripheral that is used by the ST-Link. So if you don't know, there's like the an onboard ST-Link if you're using a Nucleo board, and it uses UART communication for us to program or flash our STM32, and it uses UART communication, and the ST-Link, which is responsible for that for the PC to our Nucleo board communication, via USB uses UART2 referral. So uh, in this case, the also reason that why we use this is that we don't need any external wires for us to communicate UART, because again we are using we just utilize the ST-Link or the USB connection from our STM32 board. So select the user to and go on to the and select asynchronous for the mode. Again, we are using UART asynchronous. Um, Again, this is the setup that is used in the ST-Link, and it is also much efficient compared to using synchronous, because we'll be needing another wire for the clock, and asynchronous does fine for now. And for hardware flow control, leave it as disabled. And for the parameter settings, also leave the default values. Haven't changed anything from here. The baud rate will stick with the 115 200 baud rate, and other things right here. And also, we want to enable our DMA. So as you can see from the preview, we are displaying I'm displaying characters to our LCD via serial communication, or via UART communication, and we are using a third-party software for that, which is the real term, and I'll talk about that later. But yeah, we enter some sentence or text in our serial window, and it will then display in the our LCD. And the way we do that for the STM32 is we continuously store the data or input data that we entered again here in our real term to directly to the memory, because yeah, it is to save some CPU cycles, and not, yeah, it will not bombard the CPU, and we just want to continuously store it directly to the memory. And yeah, and also yeah, it really it really simplify things on our code and on the STM32 as well. And for you to enable the DMA, go on to DMA settings and click add. And as you can see, I have already one right here. And if you click add, this will show up, this DMA request settings. And you want to choose normal mode. If you have watched my previous videos, I normally use circular. It is because it is much more memory friendly. I mean, memory efficient in a way. Again, if you don't know these modes, okay, I'll give you the gist on this one. Whenever we use circular, uh, so again, in your code you have this buffer array, and if you use circular mode for the DMA, whenever you receive data or bytes from your STM32, it will store in your buffer array, and yeah, and directly to the memory. And whenever that buffer array completely fills up its again its buffer size, it will go back to index 0, and yeah, it will resume continuously store memory from that index. And that is much more efficient, because again we are using a fixed size of memory, and we are not really increasing or expanding our memory. So yeah, and we also don't have to worry with that, because again we are using a fixed size, and everything is just circular, and if that makes sense. And if we are using normal, we are whenever we receive bytes or data, it continuously increments our memory, and yeah, it basically logs everything whenever what we input, and that would over time that would continuously increase our memory consumption. And normally we that is not used, but in this case we are using normal mode for specific reasons. I'll talk about it later, but one thing I want you to know right now is we are using normal. It's because uh, in UART we are continuously again inputting some data, and we don't want some a fixed array for that, because uh, I mean, there would be a memory loss. Again, everything doesn't make sense for now, but I'll explain later why we use normal mode. And for the increment address, we select memory. Again, we want the direction from peripheral, the UART peripheral to memory. And the data width is byte. It's because ASCII characters are byte size. And so yeah, that's it for the DMA setting. And another thing, we want to enable our interrupts. So go on for the NVIC settings and enable both the USART global interrupt and for the DMA interrupt. Um, and that's it for the USART. I mean the UART. So we set some, I mean, we use the parameter values right here, and we use some DMA, and we enabled all the interrupts. And another thing as well is we use I2C communication for our LCD display, because as you might know, I'm using a I2C module backup from our LCD for us to interface the LCD, and that is much more efficient way to communicate uh, to your LCD personally, because it really shrinks the number of wires that you are using. And yeah, unlike from the LCD's parallel communication. But yeah, I mean, speed doesn't really matter on this one, because the naked eye really it's like perceives time really slowly. So it seems to us that the LCD character is displayed in real time. But yeah, so much so. So for the I2C, select I2C right here, and for the parameter settings, we leave everything in default. We don't really want to mess something right here. So yeah, and DMA is not really needed in this one, and the interrupt we don't need as well. So yeah, just enable it, and that's it for the I2C. And also take note of the pin setup from our peripherals. For the USART2, for the UART2, uh, it it automatically selects these pins, the PA2 for the transmission wire, and for the PA3 for the receive line. And I think you can change it, but I'll just leave it in default, because I guess this is where our SD link is connected. And for the UI2C, it chooses PB7 for the SDA line, and for the PB6 for the SDL line. And that's it for the STM32 Cube MX. And for the clock configuration, again, the board uses an external clock, and it has a default uh, clock hertz to 84 megahertz. And you could definitely tweak or change the clock source, but for the sake of this demonstration, I'll make it as simple as possible. And 84 megahertz seems to work fine as well. Seems to just work fine in the project. And go ahead and project manager, and again, I'm using Kale IDE, so I just select MDK ARM. So generate code. And before we go on to the KIDE and work the code from there, I want you to have some kind of a serial communication program. So here I'm using real term serial capture program, and you can really just search from Google. And this is like an open source program, so you can easily download on this one. And you could also use Putty. The only thing that I'm experiencing on this one is it doesn't have duplex mode. Basically, it doesn't really filter out the in the terminal, which is the on which is the receive and transmit line. So the way I like here in the real term is because it has a like a color indicator on which is the who is transmitting and who is, and another color for the receiving. So in this case, I am sending 01 command don't you worry, I'll talk about these commands later on. But color green indicates that this is the one that you are sending from the to the STM32, and the yellow, this is the response from our STM32, or this is what we received from the STM32. And realterm does a good job on really on like making it user friendly, and yeah, and it has a lot of functions compared to PuTTY. um, yeah, and you can really PuTTY, yeah, I mean PuTTY does work fine as well, but I think it lacks on this functionality on uh, displaying who is who, like who is displaying, who is transmitting, and who is sending. So yeah, I but I highly encourage you to use realterm. And but if you have PuTTY and you don't want to install any other software, then and you can just use PuTTY. Just take note that if you're using PuTTY, you are, let me just load this one. This is my setting for the STM32 via serial UART. So before, check which COM or port is your STM32 is connected. And I'll leave this to you guys. I'm sure that you know where to find this COM12. It is in the device manager, so go check on that. And for the connection type, serial, and for the speed, it's 115 to 100. So don't you worry, I'll talk about this in the real term later on. But if you're using again PuTTY, these are the the inputs setup. And in the terminal, you want to implicit CR in every LF, so that it won't uh it won't display all the transmission and receiving datas in one single line. So this is basically the purpose on that. And local echo and local line editing, you select force on. So that's it for the PuTTY. And again, for this series, or this video, I'll be using realterm. So I'll talk about the real-time setup later on when during the code. So that's it. And again, generate code, and your an open project, then your KIDE must be launched. So see you there in KIDE. So now here we are in our KIDE. So go ahead, check on your main file, and you can see um, there are different configurations here, prepared again, made for us by the STM32 CubeMX. So these are function declarations from what we configured in the CubeMX. And yeah, there's also the different handlers for our different enabled peripherals. And I'll get down back with these variables right here. And so yeah, let's go ahead and check on our main. Oh, by the way, um, since we are using an I2C, I am using an external library that I made. So I included here in my main file, and here is the different functions that you can use to control your LCD. And I've already explained this in my previous video in the multi ADC mode, where I use again an LCD display. But yeah, to briefly explain, these are the different functions for controlling our LCD for the initializations. However, the initializations here is for 4-bit initialization, and for 20 by 4 LCD. However, it can work by 16 by 2, but you can't the cursor, I mean here in the LCD put cursor, you are limited to only 2 lines. So these you are limited to 2 rows. So and here in the initialization, again, we initialize it for as 4-bit interface, because again, we are using a I2C backpack module that is hardwired for only 4 lines in a data line. And yeah, we don't really need the full 8 bits. So yeah, these are the functions. Go ahead and explore it, and also make sure that the slave address for your LCD is also the same as mine. So if you're using again an I2C backpack module of PCF8574, usually the board that the PCF8574 have is configured in this way. So go check on your manufacturer's data sheet and check if we have the same I2C slave address for the LCD. So yeah, I've already included here the that specific library. And let's go ahead and check onto our main. So first, of course, is the HAL initialization. So these are all by default already included in our code. The system clock, and again the initialization functions of all the peripherals that we have enabled: the I2C, the DMA, the UART. And here is the start of my code. So I've initialized. I call the LCD initialization, and I've cleared it the after initialization just to really yeah, to clear the display and make sure that there's no characters displayed. And I put here some kind of a introduction like display, or I would like to call it like a splash screen display. So for a brief 2 seconds actually, this message will show up: STM32 UART LCD control. And as you can see, per LCD sense string, I have initially I have set on which cursor or on which position should I place the text or the string. So uh, this is the position. Go ahead, explore on that one. And again, okay, let's go back to I2C LCD. And as you can see, the row, again, I'm using a 20 by 4 LCD, so I am limited to 4 lines and 20 columns. Four row lines. So I can only enter up to 0 to 3. So 0 for the first line, 4 to the last line, and columns for the yeah. I just XOR uh or equals it to the yeah, just enter it right here for the column. And yeah, all other explanation again is found in the my previous video. So again, this message will show up for 2 seconds, then eventually it will clear out the LCD. Then I set the default position to 0, 0, 0, first row, first column. And this one right here, I have entered here the array that we want to store our input data, our input byte. So I have declared it right here as a global because I want it to see the values during debug mode, so it can only be viewed if the variable is in the global. So which is why I put it in here. And yeah, I've set 25 bytes for it. And here, normally when you want to, so this please listen about this one. Normally when you want to receive date characters, I mean receive bytes, input characters in your UART, then store it in DMA. You want to use this function. So again, if you don't know how to locate all the functions of the HAL library, just click right here. So these are the different functions of the HAL functions, HAL library, HAL API, and we specifically want to go here in the HAL UART, and you normally want to use this one, the HAL UART receive DMA. But the case on this one, as you can see, it has the same parameters of this one, the receive to idle DMA. But the case on this one, it won't trigger a event callback let's say you entered in your here in your real term in your serial communication program the character ID text hello, but again the buffer array, which we call buff, has a size of 25 characters. Um, but we only just entered hello, then we click enter in our serial program. This won't trigger a interrupt callback because the hello only comprised only, let's say, how many it is, 5 bytes, 6 bytes, and uh whenever you use this one, UART receive DMA, it won't trigger a callback, or yeah, you basically it won't trigger a some kind of an interrupt that that there's a input data being received. It's because it will only trigger whenever you reach the um full character full bytes you have declared in the buffer, which is 25. But we only receive 5 bytes. We don't want to use this one because again we are entering different number of bytes, or let's say we just want to enter hello. We don't want to really fill up all the 25 bytes on this one so that it will trigger a callback. So um, fortunately, there's another function for that, and this is called the receive to idle. So in the receive to idle, even though you have a a memory allocated of 25 bytes in your buffer array, uh, it will trigger a callback whenever you enter a enter in your keyboard in your enter key, which is a carriage return in ASCII. Um, This is because to the receive to idle. So even though we have only 5 bytes entered in our serial program, it will trigger a callback. It's because we use this specific functions receive to idle. So again, why we use this one is that we want to enter data in our serial program, even though it's not full 25 bytes. So we can enter any amount of character. I mean, yeah, number of bytes for as long as it is not it's not above 25. So yeah, that's the reason why we use receive to idle. So I hope you understand my explanation. So again, this specific function receives two parameters: the handler of our UART, which is UART2, then our buffer array. Again, this is our array, and the number of bytes that we want to store in our buffer. So this buffer has a 25. We allocated 25 bytes for that one, and so remember that this will trigger a callback whenever we click enter on our keyboard. But yeah, so that is for the idle line, and this will call the RX event callback. This one, it will enter on this one whenever you hit enter, but it also triggers a callback if all the 25 um, is full. I mean, all the buffer size is full, so it will enter in this callback. Um, and it will even trigger the callback if it is half transmission. Let's say we entered like what's half of 25? Let's say 12 plus, yeah, around 12. It will trigger a callback, and we don't want that one, which is why so that is for the half transmission. So which is why we disabled it in the next line here, how DMA disable interrupt the DMA interrupt half transmission. So this is what it means. So I don't you worry if you are still quite confused. It will make sense later on. So just remember that there's a difference when we use this one, the HAL UART receive DMA, and this one, receive to idle DMA, because this one will only trigger callback whenever the buffer size or the array size is full. and this one will only will trigger if it's full, or even we enter we click enter in our keyboard. So as you can see, our super loop or our while loop is empty because we are using DMA, and that's the advantage of DMA. We could do anything from here um, because we are using DMA. And so now let's head on to this callback. Where was it? Event, this RX event callback. So again, this will trigger whenever there is a full transmission of the array, I mean the input data, a half transmission, and an idle line, or a whenever there's a carriage return. But again, we disable the half transmission because we don't need that one. So you want to copy this function because it's still in the weak type, and we copy this one, and then we paste it around here in your user code begin for. And as you can see, I've already have one. So this is where a chunk of our code is really going on. So I've pasted the UART RX event callback, and it has a parameter of the handler of the UART and the size received in the in our buffer. So um, so this function right here will trigger even in different UART peripheral. So as you have seen in the STM32 Cube MX, you notice that there are a lot of UART in in my STM32. In my specific STM32 chipset, I think there was about 6 or 5 UART different UART peripherals. So uh, this will trigger each one of them. So we want to in this condition, we want to really determine if the callback that is triggered is made by our UART peripheral, which is the USART2. So we pass in the UART pointer, then determine the instance. If it is USART2, we enter this if condition right here. So okay, I want to explain how this basically this project works. So I have here a let me just clear out this one. I have here a serial program. Again, I'm using a real term, and I want that if I enter, I want to control, basically I want to control the what my LCD displays. So let's say I want to enter STM. Oops. Okay, let me just clear for a while. Let me just, let's say, okay, that's good. Oh, okay. It's a bit acting strange. Okay, let me just oh, here. Here in the send. So again, it doesn't matter what program you're using, but I'm here using the real term. So I want to control my LCD in a way that I want to control on which position I want to display my text. Let's say I want to enter "Hello World" in my LCD, and I want to display it in the position of the second line, which is again 1, because the first line is 0, then the second line is 1, the third line is 2, then the fourth line is 3. So 1, then let's say the second column, which is 1. So I mean 1, 1. So whenever I enter send ASCII here, so first I want to send on which position I want to start my text. So again, this means that the first row, I mean the second row and the second column. So send ASCII, then as you can see right here, this is the one that I sent. Again, I've coupled it with the carriage return and line read so that everything will be one line per command or per instance. So I've entered this command and the STM32 responded okay. That means the command is received, and it will then display some characters on my. It will then position my cursor in that position, in that specific position, and that's the part when we enter send ASCII. I mean the hello world. So if you will notice this one in the LCD, uh, this will appear on the first line, second line, and the second column. So that's how I program this one. And let's say on the next line you want to enter let's say STM32, it will then display STM32. So again, first you want to set the position first, or send the position first, send to 1, then it will then reply okay, and hit for the STM32 send ASCII. And that's the good thing about this real timer as well, is that it caters to inputs, so that yeah. And also, why there's color right here is that the green indicates that that's the one we are sending, and the yellow is the what the STM32 sends to us, or what we receive from the STM32. So that is enabled here in display half duplex. So take that one, and again the port, uh, we are using 115 to 100 baud rate. So make sure you selected that one, and again check which on which port your STM32 is located, and select here, then click open, then it will then display here if it is connected. Then here in the send category, where you can send some ASCII characters. So let's head on to the code. I'll try to explain it how I managed to do that one. And by the way, I also have some different unique commands. Let's say there's a lot of messages in your LCD and you want to clear it out. I have a program, some command for that one. Using a $sign, then C, it will display the characters in the LCD. Just send this key. So it will automatically go into the default 00 position, and then so let's go back to the code. So going into this if condition, I've declared a pointer variable that is pointing to the first index of our array, which is buffer. So this is our array. Again, we declared it up in our global section, and again, this is where the input data is being stored. So uh, so again, we have devised a way so that we can input a specific position of our cursor, and this is the syntax on it. It has an open bracket, then followed by the row value, then comma, then column value, then closing bracket. So for example, if I've entered this one, an open bracket, then row one, row one, which means second line, then row one, column one, or the second characters from the the second character. Then it checks on this specific the first index. So if we enter this properly, it should have a should read this open bracket. And if I just an if condition on that one, if it is equals to open bracket, it will then enter in this if condition. So, and I have here a variable has comma. This is some kind of a flag if the comma character is detected, it will be set to 1 if it is detected. So now that we have let's say we have entered open bracket right here, we want to increment our address. So from here, it will then point on this value right here, the next line and the next character. So you can use some array indexes, but I do prefer using pointers. So because using pointers saves you from declaring another variable for the iterable, for the index in the array. So you do you. So then we dereference it, and if the this one has a value from ranging from 0 to 3, again the row is only limited to 0 to 3 because I'm using a 20 by 4 LCD, and if you are using a 16 by 2, you're limited to 0 to 1 only. And if the value is ranging from 0 to 3, say we have here 1, it will then assign it to the variable row. So but we won't directly store it to row because it is in the character variable. Remember that our input data is in character data type, so we want to uh, convert it into an ASCII by subtracting it to the integer value of the character 0. And so that's the way we fully extract it, for in this case 1, and store it to row. And if it is not the value is not ranging, it's not does not fit or belong to 0 to 3, it will go to this else block right here, and it will send us an error message. So let me just slide this one to the left. This will send an error message to our serial monitor or serial program. So let's say let me just reset my STM32 right here, and open, then close. Yeah, open. So have duplex again, port 1500, 15200. I'm using port 12, and click send. So let's say we entered right here 5. We know that it is only limited to 0 to 3 rows. Let's say 1, and if we enter that one, send ASCII, it will, you see, it will respond to an error message. Error, invalid row input, only input 0 to 3. Okay, but it also display okay because again it is a response from our STM32. So um so yeah, it will return some error message, and basically I explicitly enter the string message right here, and I've typecasted into unsigned integer 8, and this one has a value of 43. It just means that there are 43 characters here, so I have to manually count it, so enter it right here. You could always use the C library, the for the string. I just prefer using this one because it's a good practice to really not use libraries. I do prefer that one. I just want to make it as native as possible. And increment, then we then increment the pointer. Let's say if we just entered 1, where was it, 1, um increment that one, then it will then point to this comma. But yeah, point to this comma. So if pointer, the reference the pointer equals to comma, and we will set the has comma flag 1, then increment the pointer, then it will then point to this value right here, 1. So but we have to check if it really has a comma, because again we want the syntax to be followed at all times. So if it doesn't have a comma, because we are only expecting 0 to 3 values, not a 2-digit value. So it should have only 1-digit value, and if it does have a 2-digit value, it will then return an error message here again. So this will be transmitted to our serial program. So if it has comma, in our case, if we enter this one, it will then enter this if condition right here. Then uh, again, it is pointing to this variable right here because we have incremented the address. So if the value is ranging from 0 to 9, again the column range value is 0 to 19 because I'm using a 20 by 4 LCD, so it is limited to 0 to 20 columns. And then yeah, so if it is a numerical value and it falls to this range 0 to 9, we will then again use we dereference it, then subtract it to the character variable, character type, the character ASCII of 0, then it will then return, let's say in our case again 1, so column 1. But let's say if our value is 10 right here, so it's a 2-digit, I mean 12, 2-digit. So to store 1 right here in our column, but if we increment our pointer again, we doesn't mean we it doesn't really increment it, but if we +1 it, and if we check if there's the next address or next position, there's another numerical value, it means that we are dealing with 2-digit numbers. It is above 10, I mean above 9. So we want to extract that value by multiplying the the second digit by 10, then add it the ones value, or the ones value. So this is the tens value, the ones value, then this is the one. This minus 48, this can also be this one, character 0, but yeah. Well, I don't know why I'm using the 48 right here, but this will return, in our case if we enter 12, this will return 12. Then we increment then the address, and it should have a closing bracket upon the reference. So, and if column, let's say if we enter like 22 right here, we know that the value range is 0 to 19, and if it is above, then it will again put some error message, enter range message. So that's it. And for the row, oh yeah, this one, if we don't put a comma, it's not a row. So yeah, that's it. And increment, and then if we detect a closing bracket, it means that we have completely read the command, and it will then reply okay. So it means that we have read a command. And this one right here, whenever we enter OK, we want to append some carriage return and line feed at the end, so that it will look nicely and neat in our serial program, so that whenever we input something, it will then input on the next line, thanks to this carriage return and line feed. So we explicitly put it or append it in at the end. These are the ASCII values of the carriage return and line feed. And then we set up the row and column values based on what we have extracted from the command. We then send it to the command LCD put cursor. Then we transmit the OK response to our serial program, and then we will then revert back to the first position of our buffer. So yeah, and then we want to, after every time we again we entered some data and place it into our array, we want to, after reading the command, after reading the command, we want to empty out our buffer, I mean our array. so that yeah, we want to make it so that yeah, we just want to clean out our array afterwards, because we don't want to pile up every time we input in our array. So we empty out by placing some zero values on it. And then so I've also have like programmed it in a way that we can clear the LCD, because every time we could display some text in our LCD, but it's just a matter of time where we completely fill up like our LCD, and it will maybe it will get messy later on. So I have configured some command on here. So if we put a dollar sign then followed by C, it will clear the LCD and revert back to the cursor to the first column and the first row. So by using this command, it will clear the LCD. And else, if it is not a cursor command like this one, if it's not this, or if it is not this one, it is not those two. If it's not those two are the input, then it must be the message that we want to display. So it will go to this block. So pointer plus plus count. So this basically count the received bytes, because in the how you are transmit, it is a requirement to pass the number of bytes we want to transmit, and we again the buffer size has 25, and maybe again if we only just put less than 25, um, uh, yeah, at the end of it will just be completely null, and we don't want to transmit those null values. So we just yeah, count the number of characters, then transmit it in the our UART, and this will be uh, sent to our serial program. This will be then displayed here. And then we also send string. We send the message to our LCD. So again, the I2C communication, the I2C HAL will be displayed here in the different library. And yeah, just take note. It is just quite similar to UART transmission. Um, the what do I mean, the HAL, the function and the parameters that are being passed. And again, afterwards, we clean out the buffer, so that we can again we to avoid piling up all the input datas. And that's it. And I think it's pretty much straightforward. Again, you can just use, I mean, this is not really the fully optimized code. You could just use a string library, but I do prefer this one because it is, again, it's more like of a bare metal approach. And also I'm using pointers, so that yeah, just to practice out my pointers knowledge as well. And yeah, and by every time we receive a callback, we want to resume our receive to idle again. So this is like to start once again the receive to idle, because if we don't put this one, it will only, the program will only receive one input data. Then it won't then it will not further receive succeeding input data. So we want to start it once again. Then same thing here, we want to disable the halt and the half transmission. So that's it. Again, the big chunk of our code is found here in the Rx event callback. And let's see in our code. So go ahead, save this one first, then build, then I'll flash it into the STM32's memory. So after flashing the program, go ahead and open your serial program and go to display half duplex, tick that one. So again, if you are using realterm, then go to port, select the baud rate 115 200, and my STM32 is connected at port 12. then click open on that one. So under here in the sand. So okay, let's test this out. But first, let's reset our STM32. So let me reset that once again. It just displays garbage message right here. You see that? It does that once in a while, but if I reset it again, there. So it shows the STM32 message for 2 seconds, then it then reverts back to zero, put zero column and zero line. So okay, let's test this out. So first we send some command. So here I have some history input data. So if I enter column 0, I row 0, then line 1, column 1, then send ASCII, then the STM32 then responded OK. So it means that the STM32 received that one, that command, and then it sets the position then the LCD in the first line, then second column, and we send the message hello world. So as you can see, it displayed in the LCD. So let's just test out displaying hello world in different in all lines. So let's say 1 second line, send ASCII, the STM32 responded OK, then hello world. So you can see it displayed in the second LCD. And let's say the next line, which is 2, let's say in the right indentation, say 9, send ASCII, sets the cursor, then send the message hello world. Then say the next line, the last line, 3 9, send ASCII, then send hello world. So as you can see, all lines has been entered hello world in different one from the left side part and the right side part. So as you can see, the LCD is quite messy and needs to be cleared up. So the way you do that, just enter the $C, send ASCII. It will then clear up the LCD. So that's how you do it. And yeah, that's it for this video. And now you can enter and control some the display characters in your LCD using this one. So I hope you enjoyed the video, and thank you for watching.